The Earth's North Pole is not a fixed point. Unlike the South Pole, which is situated on a solid landmass, the North Pole is located in the middle of the Arctic Ocean, amidst waters that are almost permanently covered with constantly shifting sea ice. It is always moving, drifting slowly across the Arctic. This movement is influenced by complex factors, including the Earth's molten outer core, ocean currents, and even the gravitational pull of the Moon and Sun. For centuries, we have used the North Pole as a fixed point for navigation, mapping, and understanding our planet. Early explorers relied on it to chart their courses through the treacherous Arctic waters, and it has been a crucial reference point for scientists studying the Earth's magnetic field. But this point, once considered static, is now shifting at an accelerated rate, forcing us to reconsider our assumptions about the very ground beneath our feet. Recent studies have shown that the North Pole is moving at a speed of about 10 centimeters per year, a rate that has increased significantly over the past few decades. This movement, though subtle and largely unseen in our daily lives, has profound implications for our technology, our climate, and our understanding of the planet we call home. Navigation systems, communication networks, and even power grids can be affected by these shifts. As scientists continue to monitor the wandering pole, they are uncovering new insights into the dynamic nature of our planet's interior and the forces that shape it. One of the main drivers of the shifting North Pole is the melting of glaciers and ice sheets, a consequence of the warming climate. As global temperatures rise, the ice that has been stable for millennia begins to melt at an unprecedented rate. This melting is not just a seasonal occurrence, but a continuous process that is reshaping our planet. As massive ice formations melt at an alarming rate, the weight distribution on the Earth's surface changes. This redistribution of mass causes the Earth's crust to respond, leading to shifts in the planet's axis. The melting ice contributes to rising sea levels, which in turn affects coastal regions and ecosystems. Imagine a figure skater spinning with their arms outstretched. The skater's spin is steady and controlled, much like the Earth's rotation when its mass is evenly distributed. As they draw their arms in, their spin accelerates. This is due to the conservation of angular momentum, a principle that also applies to our planet. When the distribution of mass changes, the rotation speed and axis can be affected. Similarly, as the Earth sheds its ice burden, its rotation is affected, causing the poles to wander. This wandering is not random, but follows a pattern influenced by the redistribution of mass from the melting ice. This phenomenon, known as glacial rebound, is a slow but steady process that has been ongoing since the last ice age. As the weight of the ice is removed, the Earth's crust, which was previously compressed, begins to lift and adjust. However, the rapid melting of ice in recent decades due to global warming has significantly accelerated this process, making the adjustments more pronounced and quicker than in the past. This acceleration has profound implications for our understanding of climate change and its impact on the planet, contributing to the faster movement of the North Pole. The shifting pole is a clear indicator of the dynamic changes our planet is undergoing, driven by the relentless force of climate change. Understanding these movements helps scientists predict future changes and their potential impacts on our world. Deep beneath the Earth's surface, the planet's molten core churns and flows, creating a dynamic system that also influences the position of the poles. This molten core is primarily composed of iron and nickel, and its movement generates the Earth's magnetic field. The core's dynamic nature is a key factor in the shifting of the magnetic poles, a phenomenon that has intrigued scientists for centuries. This process, known as mantle convection, involves the slow movement of hot molten rock in the Earth's mantle. Mantle convection is driven by the heat from the core, causing the hot material to rise towards the surface, while cooler material sinks back down. This cycle of rising and sinking material is crucial for the transfer of heat from the interior of the Earth to its surface. These movements, driven by the Earth's internal heat, create a sort of planetary conveyor belt, with hot material rising and cooler material sinking. This conveyor belt is not only responsible for the transfer of heat, but also plays a significant role in the movement of tectonic plates. The convection currents act as a driving force, pushing and pulling the plates in different directions. This constant motion exerts subtle but persistent forces on the Earth's crust, causing the poles to drift over geological timescales. The drifting of the poles, also known as polar wander, is a slow process that can lead to significant changes in the Earth's magnetic field over millions of years. Scientists study these changes to understand the history of our planet's magnetic field and its future behavior. Furthermore, the Earth's crust is broken into several massive tectonic plates that are constantly shifting and colliding. These tectonic movements are responsible for the formation of mountains, earthquakes, and volcanic activity. The interaction between these plates can also influence the position of the magnetic poles, adding another layer of complexity to the Earth's dynamic system. These movements, though extremely slow, can also contribute to the polar wander, adding another layer of complexity to this fascinating phenomenon. The study of polar wander helps scientists to understand the intricate relationship between the Earth's internal processes and its magnetic field. By examining the past movements of the poles, researchers can gain insights into the future behavior of our planet's magnetic field and its potential impact on life on Earth. Navigation systems rely on precise measurements of the Earth's magnetic field, which is anchored by the magnetic North Pole. As the magnetic North Pole shifts, it affects the accuracy of compasses and GPS systems, requiring constant updates and adjustments. These adjustments are particularly important for ships, aircraft, and other vehicles that rely on precise navigation for safe and efficient travel. The shifting poles present a constant challenge for cartographers, who must update maps and charts to reflect the changing positions of the poles. The shifting poles also have implications for our understanding of climate change. Climate models rely on accurate data about the Earth's geography, including the location of the poles, to make predictions about future climate patterns. As the poles move, these models must be adjusted to account for the changing distribution of ice, ocean currents, and atmospheric circulation patterns. The shifting poles add another layer of complexity to the already challenging task of predicting the impacts of climate change. Section 6. Satellites and the shifting sky. Many satellites orbiting our planet use the Earth's poles as reference points for their orbits. As the poles shift, it affects the positioning and operation of these satellites, requiring adjustments to their trajectories and data collection systems. These adjustments are crucial for maintaining the accuracy of satellite-based navigation, communication, and Earth observation systems. The shifting poles highlight the interconnectedness of our planet's systems and the need for constant adaptation in our technological infrastructure. Section 7. Rising tides, shifting sands. The melting of glaciers and ice sheets, a major contributor to the shifting poles, also leads to rising sea levels. This poses a significant threat to coastal communities around the world, increasing the risk of flooding, erosion, and displacement. As sea levels rise, coastal communities must adapt to protect their infrastructure and way of life. This may involve building sea walls, relocating homes and businesses, or restoring natural coastal habitats that can help mitigate the impacts of rising seas. Section 8. Adapting to a moving target. Thankfully, advancements in technology and our understanding of Earth's dynamic systems are helping us adapt to the challenges posed by the shifting poles. Scientists are constantly monitoring the poles' movements, using GPS, satellite data, and other technologies. This data allows us to make necessary adjustments to navigation systems, climate models, and other infrastructure. By improving our understanding of the forces driving polar wander, we can better predict future changes and develop strategies to mitigate their impacts. Section 9. The future of the pole. The Earth's North Pole will continue to move, a testament to our planet's ever-changing nature. While this presents challenges, it also reminds us of the Earth's dynamism and our need to live in harmony with its rhythms. By embracing scientific understanding and technological innovation, we can adapt to these changes and ensure a sustainable future for generations to come. The shifting poles are a reminder that we live on a dynamic planet, and our understanding of it must evolve as well.